too.
So I wanted to begin class. I was going through my grade book over the weekend, and I don't know, I have missing homework assignments from students in both places, but I didn't know if those in Daytona Beach had sent it to the wrong email address again, or... Not this time. And so far I have one quiz submitted from Daytona Beach. Okay. I did want, but before that, and I know that there's some circumstances. I noticed there was some issues with access denied for writing. I had that in an email from Daytona Beach, and I know we encountered it from one of my students here as well. That sounds to me, I've not encountered it, but it really sounds to me, one of our students here also agreed, saying that it's a permissions problem. You might check the permissions within the WECA folder,
Just the whole WECA folder.
the whole WECA folder, to make sure that the permissions are open for reading, writing, and executing.
Did you have to change the path on it? Or
I just literally, I opened up the properties and just changed.
As administrator, change the
I changed it for all of
the settings.
Yeah.
But do it with
Right, do it with the folders.
Yeah, so just open my computer, go to the programs file, click on WECA 3.0.
That's a common, it's amazing how many times when you're playing around with this sort of stuff or experimenting with these programs, that you actually have to change settings, and it's the same sorts of things that we started the class with, getting everything in the proper formats. We encountered that with the UCI repository in order to import it to begin with. So does that, was it, I'm sorry, I can't remember your pronunciation. L-E-Y-D?
It's like lady.
It is lady? Okay. Were you having some of the access?
Yeah, but I'm going to check right now to see if, what you said about the properties, to see if I can change it, and see if that fixes the problem.
Okay. Because I mean, as soon as you see access denied, to me that just rings bells of being permissions.
Okay.
So, okay. So we're going to begin. I have to add some content here. If my mouse behaves. Actually, I'm going to do this first. Okay, should be almost there. Uploading agenda contents to server. And I usually need to do this ahead of time. Why is it taking forever? There it is. Okay. So, back up. Where did we leave off? Beyond there, so we're still in association rule learning. So I think we left off, we talked about hashing, basically putting as we come across the association. So I want to kind of review, because it's been a few days since we've gone over association rules, and let's make that full screen. Maybe I should back up even further than that. So we talked about the general algorithm. We talked about how to generate. So recall the general algorithm we had. First of all, maybe it even refreshes our memory if we start talking about association rules compared to classification to begin with. So does everyone remember the general problem of association rule learning? Cody? What's different between it and, say, classification?
Between association?
Yeah. Association versus classification. Nick?
Didn't, like the association, it did the pruning? Or...
Okay, that's an algorithm, but what is the general problem that we're after?
Trying to see which attributes work best with each other.
Okay. James, you're going to read it?
Yep, discovering interesting relationships between attributes.
So we're basically looking, so think of the market basket problem. You're looking for when items occur together. That's one way to view it. A rule that says we see this item, and so then this other item may occur frequently with it. So it's co-occurrence of items. You can also, I was about to say that, but you can view that if you think of text classification. That's a classification problem. But sometimes part of that will be you see words together such as banks and money. Those you would think might occur frequently together depending on the meaning of banks there. bank being a financial institution versus, say, Bank of a River. But, I mean, those two words might occur frequently together. Or students and grades, as another example of words that might occur frequently, relatively frequently together. So in association, instead of trying to classify a student as some particular group, what you're trying to learn are associations between students and say other attributes such as grades. And trying to just learn about the frequency of co-occurrences, so to speak. So in working through this problem, the association rule problem, we've been talking about, in particular, a particular algorithm, the a priori algorithm, where we had several subproblems. One of the first subproblem we encountered was generating frequent item sets. So those, amongst all the list of transactions, you're looking for the item sets that occur frequently. If you remember, so item sets can be subset of or subsets of the big item set of all your items. Okay. Does that remind everyone, ring bells about what the problem we've been looking at? So Eric?
I said, uh-huh.
Uh-huh.
Uh-huh. Is there a new?
So, so that was the problem, and we encountered some difficulties, namely the computational complexity problem that we wanted to handle. So we started investigating a particular algorithm called the a priori algorithm. We essentially came up with a way, actually a couple of different approaches for handling the complexity of generating frequent item sets. Does that put everything back into context?
See.
So then we started looking at the general a priori algorithm again. We said here, look, we've done the problem of how to generate the frequent item set. So now we want to look at the next subproblem, which was counting the support of each candidate. So that's what we're looking at right now, is how do we efficiently, and so to save a lot of time and computing resources, count the support at each candidate, and then eliminate infrequent candidates. So just to step back and proceed fresh, we said, okay, one approach, brute force, usually not the most efficient, and it's also not that efficient here. It's computationally expensive. So we went through, and I can't remember where we went here. So enumerate only those item sets contained in each transaction. Then as you go through transactions, only update the supports of each of those. So as you come across a transaction, say it has 4 items, and you're looking at this point as your subproblem of updating item sets of size 3. So in that case, you're only going to update 4 possible item sets with that transaction. You're not going to look at all the possible item sets. And that's fairly easy to do and not that time consuming even as you go forward. We talked, and I'm not going to review too much here, but we talked about how to enumerate your 3 item sets. We use this tree diagram here to kind of say, if you're looking at 3 item sets, the first, supposing they're in order, the first bucket, so to speak, can only be one of the first 3 terms if you have 5 terms, or it's actually, it depends on the size of the transaction. This is kind of a toy problem, but you want to only be 3 from the end. So you don't even have to start looking at, say, 4 or 5 being the beginning. So it's just an efficient way of counting through your item sets. We very briefly went over the hashing algorithm. Here we did mod 3, or the size 3 item set, to put things into the different groups. I don't want to spend too much time on these details, so I just want to kind of refresh the memories. Any questions about how we did that? Jeremiah? Oops, I think I skipped. Okay. We did talk a little bit. How did that? Okay. So we're going to try to continue here. So we want to talk a little bit as we move forward. Trying to remember why this was where it was. So now we still want to, right, because what we're going to do is we're going to start pruning based on confidence. We previously pruned based on support. I don't know if you remember that. That goes a ways back. We can come back to that when I get to a particular picture that'll show what happens when you prune based on confidence. So suppose you're generating rules. One thing we can do is partition an item set into, again, an item set of size k. We can construct the item set and the complement y minus the item set. So we'll construct a subset x and y minus x, and we're going to look at all the association rules. So remember, the goal in association is to generate these rules, and then we want to count their support and confidence. So we're going to just consider these partitioned, the rules coming about from partitioning the item set. So if you've got, say, a 3-item set, you can have a rule going from an item set of size 1 to an item set of size 2, or vice versa. And so those are going to be all the rules you'll look at. And what we're going to be interested in is, so now we've computed these different association rules, we want to then calculate their support and confidence. And that's actually fairly easy because the support values were calculated when we generated frequent item sets. So this has already been done, and the support is what gives you your confidence values. We'll I'll get to that as well as a later stage, but basically it's the support of your intersection of your sets over the support of, so it's this, it would be the support of the result over the support of your assumption. And we've already got those values, so those are easy to calculate. And so then we can prune our trees based upon confidence as well. Before, when we generated frequent item sets, we pruned those based on support. I don't know if you remember that. Or am I just talking to? You remember good?
I'm trying to remember what.
Oh yeah, I remember.
That was it was that diagram. I don't want to lose my spot here, but it was it this diagram here?
Yeah, big it.
Or if
I
things
found it.
didn't meet a certain threshold or frequency.
So it was.
So this one.
So in this example, when we generated frequent item sets, notice we had this lattice of subsets, right?
So everything else.
And notice we found AB to be infrequent. And so that allowed us to prune this whole branch of subsets from our lattice,
Yeah, it took like a fourth of it away.
right? It's because the subsets, so because a set was found to be infrequent, then all these subsets of that set were also. Or subsets or
Subsets.
So if you cut out-
supersets.
You cut out A.
Supersets, because this has ABC, this has AB.
Yeah, cool shirt.
If you cut out, like say A was, you would just cut out everything with an A.
Right. So if A was found to be infrequent, frequent, then all the way out to ACDE, ADE, AE would have been cut out. Even more than a half there. So because when you have, say, a frequent item set being infrequent, then all item sets containing that item set would also have been pruned. So that was done in the frequent item set generation.
So why was it determined that AB was infrequent?
Well, you would go through and count
I think it's just.
how often A and B appeared in item sets.
That's like we do with the eggs.
And if A and B are infrequent, then because they're contained in A, they're counted when I count A, B, and C,
Yeah.
then ABC has to also be infrequent.
That's why we did like the grocery cart with like the Coke was only one.
Right. Coke was only one, so all the supersets containing Coke would also be eliminated.
So like if Coke was A, you cut out everything that had.
Right.
Got it.
Okay, that was in the frequent item set generation, right? That used the support of, in this picture, the set AB, and that pruned that. But now we're on a different problem, where we're using similar ideas, and this is,
Keep going.
I'll start here, okay.
That's it. That's what-
Questions, is that clear in Daytona Beach? I don't see the hand going up, so I'll presume that's a yes. So that takes us back. So the key idea is, notice, here's the confidence pruning we're going to use. So it's going to be kind of a reverse process. Okay? And I'm going to come back at the end to kind of big principle ideas here rather than the details of the algorithm. So hold on. But the confidence pruning is based on the following theorem, that if this rule x to y minus x does not satisfy the confidence threshold. Now here, notice instead of supersets, I'm looking at subsets. So what this means is that it can't be true that a subset of the rule, where x is prime is a subset of x, that must also fail to satisfy the confidence threshold. So notice the kind of symmetry here. Before, for frequent item sets, it was the supersets that got pruned. Here we're looking at rules, and we're starting with a rule of, say, set x, and if the rule from x doesn't satisfy the confidence threshold, then there's no way that a subset of that rule will also satisfy it. So a subset, so if x fails to satisfy it, then the subset also fails to satisfy it.
How do you know if it satisfies the confidence or if it does not?
Well, you can, okay, we'll calculate the confidence, and because you already, right, okay. So backing up here, when we generated, so it's this, the third sub point here underneath partition item set, when we generated the frequent item sets to begin with, we counted the support. We calculated the support. That's how we were able, the support being how many times it happened. That's how we pruned the generating or the frequent item sets. So we already had those values, the number of times this particular subset appeared.
Okay.
Confidence is calculated from those values. Confidence of a rule is given by the support of your subsequent, your implied result over the support of your left-hand side of the implication. What's that called? Not the subsequent, but it's your assumption. Antecedent would be afterwards. Your precedent, yeah.
Anti-president?
Semantics. The thing before the arrow.
Right, the thing before the arrow. So we already have those confidence values, and we've set a confidence threshold. And so if a rule is pruned, then we prune again as the following shows. Notice the reverse here. So here we've got, say, the rule, a low confidence rule, B, C, and D imply A. So if B, C, and D imply A does not have high confidence, it's a low confidence rule,
So in other words,
then so is any subset of B, C, D implying its complement, something like CD implying AB, or D implying ABC. Those will all, remember the form, X implying Y minus X. Okay. So all of these kind of sub rules will be pruned as well. So that's another way of just trying to eliminate or simplify our complexity.
So would you use all of those internal nodes as rules or just the leaf down at the bottom?
All of these grade ones.
Well, no. So those ones got cut out. I'm talking about the white ones.
The white ones, we would keep all of these here.
But would you use all of those rules? A, C, and D implies that B.
Right, those are still allowed rules.
Those are still allowed? Okay.
Right.
Just as long
So
as
we
they're
want,
not-
we'll calculate the support and confidence of those.
They're allowed because they're not implying A. If
They're
they
allowed
were
because they're
implying-
not low confidence.
Oh, okay, so.
So
even if
once I
they're
have
implying-
one low confidence, I'm able to prune out a whole section and hear about half of the rules.
Okay.
It's just a way of trying to keep things manageable. Okay. So, with the, I'm coming to kind of big picture points, right? So with any, and this holds not just for association rule, but learning, but also for classification. We're going to need to handle computational complexity. And that's kind of the curse of dimensionality and size of data problems that we're dealing with. And so, in particular with the a priori algorithm, a few ways we can handle that is changing, your support threshold, right? If you increase your support, you're going to have fewer frequent item sets to begin with, right? So you eliminate, I mean, if your support is super high, then you might not even have any item sets that satisfy that support. There's a trade-off, right? I mean, you can make it too high and then, well, now you have no roles. So, so you can adjust your support threshold to something that's manageable but still allows for reasonable numbers of rules to form. The computational complexity comes from the size of your main item set, the number of items in your supermarket, in the market basket example. The more items that you're going to allow, well, that's going to grow the computational complexity, because that the number of subsets you can have. The number of transactions that you're going to look at. So you can, all of these are things you can limit and scale to the problem at hand. Right? I mean, even when we went through the WECA problem on the quiz, you noticed that for some algorithms, we started off, I said, try to do 10 iterations. Well, we limited that to 5, just for time constraint problems. These are the same kinds of things. You can reduce the number of transactions you're going to look at. How many different market baskets? You know, how many different, are you going to look at 10,000 or 100,000? And the average transaction width, here the average size of, well, the number of items in a particular, average number of items in a basket. Now, some people might buy one item, and then you get behind the person and you have one item, and of course you're in the supermarket and you're behind the person with the whole 3 shopping carts in front of you, right?
So,
10 items or less line.
Pardon?
10 items or less line.
Yeah, how often does that really work?
It's 15, not 10, usually.
so you average the
Yeah, we have
transactions.
15
Size.
people in line, 15 items or
Right.
less.
So some things we looked at here, and these are the things, these are particular to the algorithm we just looked at, but notice what I want to really, the takeaway here are kind of ideas that we applied to the problem. So one of the things we looked at was hash-based item set counting. So grouping things into into buckets. And then doing also an efficient way of counting items, right? Instead of just haphazardly do it, can we be methodical and think through an efficient way to count? We can transaction reduction, eliminate transactions with no item sets of particular sizes. We talked about partitioning the rule, the item sets, and we were able to use that to prune whole branches off. So if you can find ways, and this is what I'm trying to get to, kind of these concepts apply to a lot of different types of problems, not just this one, right? Can we find things that will automatically eliminate whole branches of search? So these, might come up in discrete as well. Some other ideas we can apply. Instead of looking at the entire set of your data, you could sample it, right? And so you could do some random sampling of your data sets. Maybe do it, 10 iterations or however many iterations, randomly choose that. In fact, if you look at a lot of what we've done before, we've used this sampling idea for and dynamic item set counting. Add new candidate item sets only when all of their subsets are estimated to be frequent. So otherwise, you won't add those candidates. So those are just some ideas for improving the algorithm that we have. Now there's a whole nother way to look at generating frequent item sets. FP, or frequent pattern growth algorithm. I don't know if we should go over this today. Well, sure, we can get started on it because we have about 10 minutes. The big idea is to take our database, our huge database of market basket transactions, and compress it into a particular type of tree, a structure called a frequent pattern tree, or FP tree. We want it to be highly compact, highly condensed, but complete. And the idea here, I'll go through an example of how this works, but it's a complete alternative approach, a completely different approach to the problem. I think I have some examples. So the basic ideas, this uses more of that divide and conquer methodology. We're going to decompose our mining tasks into smaller ones. So, in fact, we're not going to do the candidate generation to begin with. We're going to basically start with a tree. So, here is kind of how we might start the tree. We're going to start with our null branch at the beginning, and basically we're going to go through. So on the left-hand side here, up at the top, we've got our transactions, and we can see exactly how this tree is being formed. So, as we go through here, notice that A appears in exactly 7 of the 10 transactions. And so that, as the first, notice these transactions are in order. Right? So A appears by itself 7 times as the first item in the transaction. As the first item, B appears exactly 3 times. 7 plus 3 is 10, so we've got everything. No other items starts. So we've got A appears 7 times, B appears 3 times, so we've got a split on the first position. So now, AB, of the 7 times A appears, AB appears 5 times. A followed by C appears in transaction 3 1 time. And A followed by D appears number 4, immediately by D, right? And so is it clear how this whole tree is, this is our initial tree? James?
You would still do this if you had like 1,000,000 data points?
Right.
Yeah.
Now this is the presumption here, and this is huge for those who know about sorting, is that everything's been sorted already, right? It's already in an order.
Yeah. A, C, D, oh, beautiful.
Okay? And then notice we've got these pointers between, just to help us out here. So B points to B, which points again to B here. So you've got these connectors.
And it has to be sorted to do this tree.
Right. Now, this is just, this slide I just threw in here, that is going to depend upon how the item sets are ordered. So the tree that we end up with will change if I wrote the order instead of A, B, C, D, E, E, D, C, B, A, or some other particular order. So you're going to end up with a different tree. So that is something to be aware of with this particular method. So here's how we're going to basically, and this is, again, I want not necessarily the details for you to understand the nitty-gritty details of all of these, but just kind of see the bigger outline of this divide and conquer approach. Look, we have this big problem. Can we decompose it into, at each stage, smaller subproblems? So what we are going to do here, is somehow these, here's our, we're looking at, say, this tree here that we had A, B, C, D, E, and somehow the numbers don't align. I thought that
They're different than the one in the book.
Are they?
Yeah, because the one in the book has A, 8, and B, 2.
Well, that's what's on these ones. No.
Well, yeah, this one, but the previous slides are 7.
The previous slides had 7,
And these all have 8.
and those had 8. So
There just must be a different data set.
This would take a while.
yeah, but it's actually I don't see that. Where A became 8.
Because this is our data set in the book.
You really just change the data set.
Oh, I guess I got it from the 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I have a different tree there. Yeah, I think I used a different starting point. And it's not that one,
That's different.
and it's not that one. Instead, we had A8 and B2, and then everything else looked the same after that.
7 is supposed to be A, not BC.
Pretty funny.
So this should be an A8 and
No, no, no.
B2?
Your ID 7, it should be just A, not BC.
I have a BC.
In 7.
Number 7 in the,
That should be A. Just A.
Oh, number item. Okay,
That's
I don't think it matters.
right, but that's gonna make a change, so.
Yeah.
So instead of 7, we'll have 8 instead of, so I have a different, slightly different data set. What I can do is I'll pick up with this, with the correct version next time, so we can see exactly how this whole system works. Again, I'm not as interested in the nitty-gritty details as that you understand what are kind of the ideas and concepts we're using to make things easier. Okay.
Good.